How's it going?
Are we on?
Looks like it.
All right. I see the audio feed is all loud and clear. Hey, scoot over, scoot over. Okay, cool. All right, cool. Welcome, everyone. I'm in the camera. I'm in the shot. All right. So this is ISE, Independent Security Evaluators. We have another live stream today. I'm here with my colleague, Shaun Mirani. So that was a cool jinx. So ISE Labs is doing a series on different a research project on a bunch of embedded electronics, IoT stuff, routers, NASs, all that good stuff. Today we have what device?
The ASUS RT-AC3200. I know it's a mouthful, but it's basically just this ASUS router.
Can you hold it up without disrupting it? Oh, look at this. Wow, it's a real big spaceship. All right, cool. So we're gonna see that device today. We're gonna see some new vulnerabilities that you and the rest of the research team worked on.
Yep.
I encourage all of you to check out the blogs associated with this project. So you can make sure to see in the description below, you're going to be able to see the links to our Twitter and to the blog and everything like that. So you can get detailed read-ups on this stuff and also get updates. Make sure to smash the like button, do the bell, subscribe. I don't know. That's what the YouTubers say. So with that, what exactly are we going to be able to see today, and what sort of process will you show them?
So today I'm going to showcase the process of building an exploit that chains two vulnerabilities for this router. Now, one of them is a buffer overflow that actually turns out to be unexploitable on its own due to ASLR on the router. Now, if anyone doesn't know what that is, that's Address Space Layout Randomization. So basically, when the router launches a new process, it loads the different sections of the process at randomized addresses. And that makes it hard for an attacker to figure out where useful code and data are going to lie. Now, the other vulnerability we have is a uncontrolled format string. And using that vulnerability, we can leak information from memory and use that to help us and assist in the buffer overflow exploitation. And that actually enables us to get a root shell on the device.
Okay, so what sort of is this a common device people are going to find in their homes? Is this a consumer, or is this small office, home office? What are we looking at?
Yeah, this is a Soho router, typical Soho router. It's something you're going to find in people's homes, in small offices. The thing is, though, about these vulnerabilities is they're not extremely valuable from an attacker's perspective in the real world because they require authentication.
Okay.
So the primary reason we're talking about this and doing the stream today is to discuss the technical aspects of the vulnerabilities, independent of how effective they're going to be for an adversary in an actual, who's actually targeting one of these offices or homes.
Yeah. And even if this wouldn't be the direct method to getting access to a network, they would have to get a full foothold on the network to even get to this device some other way.
Yes, so this vulnerability, well, these two vulnerabilities are only accessible from the LAN by default, unless you have remote administration enabled on the router, which we don't recommend you do at all, because that opens you up to a world of attacks. Then this exploit is not going to be effective against your device.
All right, cool. So pretty much the people at home are going to be able to check out sort of the methodology that we use here at the labs when doing research. You can apply this methodology doing your own research. Some of the stuff you'll be seeing can certainly help you and where you want to be in your career or just having fun when doing independent research. Also, how far along are we on the disclosure process with these?
These have been disclosed a long time ago.
Okay, cool.
Back in the summer, I believe. So yeah.
And do we know about any sort of updates or patches pushed out?
Yes, ASUS has pushed out patches. The weird thing is they did not push out updates for this specific device. They pushed out updates for the firmware that runs on other devices, but not this model. And we asked them about that, and they didn't get back to us. That was several weeks ago. So we're just going to assume that they'll take their time with that, whatever. But there is an update available for, it's called ASUS WRT is the firmware that these use.
All right.
And so it's all patched in there, just not for this RT-AC3200.
Okay. And is some of the stuff you found in this device, because it's an ASUS device, cross-platform?
You mean it applies to other devices?
Yeah.
Yeah, it applies to anything that runs the vulnerable versions of ASUS WRT that uses HTTPD.
Okay, so even if you have another version, you know, you could still encounter these types of issues just because they use a platform for the same firmware.
Yeah, they use the same firmware, and even there's this custom firmware thing called ASUS RT Merlin. It's like for people who like to customize their routers, download this firmware. It's a little bit better than the stock firmware, but that turned out to also be vulnerable. But they did push out a fix for that.
Okay, cool.
So if nothing else, you could always use ASUS RT Merlin to patch yourself from these bugs.
All right, cool. But once again, this is definitely not going to be like, you know, someone just on the internet has remote access to your machines. This is definitely going to be taking a look at our research process and sort of finding bugs on embedded electronics.
Yeah, the world isn't ending here. No hype here.
All right, cool. But it should be a lot of fun to check out. And with that, I'll hand it over to Shaun. He's going to take us through, walk through step by step. You're going to be able to see our entire process and hopefully you learn a lot.
Yeah.
Awesome.
So here we go. Let's get started. There we go. Now I have my screen up. So this is the administration portal for this device. It's pretty straightforward. Looks nice. You can see this is the exact firmware version we're running. This is one that happens to be vulnerable. So we're not going to be spending a lot of time here on this web page because it doesn't have a lot of stuff that's really relevant to our vulnerabilities. Most of the time it's going to be spent in GDB or even in Burp Suite. So I will say about this interface, though, is that it's handled by software on the router called HTTPD. Now, it's this like really old web server, custom written for maybe a router that was adopted by ASUS, and it's from 1999 at least. It's really fun to look at because you find all these like suspicious-looking code patterns that may lead to vulnerabilities, and that's actually how I found some of these bugs. Now, in the interest of time, I'm not actually going to go and show you how I found both of these bugs because I don't want this to be an obnoxiously long stream, and the process of actually going and exploiting them is time-consuming enough. But I will show you what they look like in source code because we have that thanks to ASUS's GPL release policy, as well as I'll show you how to build an exploit for them and run it against the actual router. So yeah. Just to give you an idea of what the router looks like in Burp Suite, once again, this isn't entirely relevant to what we have for these vulnerabilities. It makes a couple of requests every so often to ajax status.xml, update network, mapd.asp. Once again, not relevant, so I'm going to move on to source code. So like I mentioned before, there are two vulnerabilities that we found that enable exploitation to get a root shell. The first one is a lot more straightforward than the second one, so I'm going to go ahead and explain that first. So we're inside the source code for HTTPD here. It's a lot of files. Well, not a lot, but there's a few written in C, some header files. And the main ones you need to know about are httpd.c and web.c. httpd.c basically takes in incoming requests and like parses them out into their headers. So for example, well, you get the idea. So like handle request. So it has a buffer for each line of the request, and it basically just parses it out into the version, the protocol, the host name. Pretty straightforward stuff. This actually didn't have a lot of vulnerabilities from our testing of it. That isn't to say there aren't more, but most of the vulns we found were in web.c. So this is like all the specific protocol handling stuff for ASUS. Like their entire API is built in web.c. And the first vuln that we found is the uncontrolled format string, and that comes from EJ NVRAM match. That's a RPC handler function. So basically, there's this endpoint at /appget.cgi, which I can show you in the browser. it's sort of like an API almost, except you give it like a function name, and that corresponds to a function in source, and you give it the parameters that it requires, and it returns some response in this like weird, not quite JSON, but not quite like HTML or anything like that response. And EJ NVRAM match is just another one of those handlers for this API. NVRAM is like, it's random access memory, but it's non-volatile, hence the NV. So it's storage for the router that persists between reboots. Now this function, all it does is it takes key. In this case, they gave us a nice example in the comment here. WAN proto is the key, DHCP is the value, and a string. If the router checks its NVRAM storage and WAN proto maps to DHCP, it's going to print out selected. So pretty straightforward right here. Now the devil's in the details, and the problem with what they did occurs here. Don't mind this debugging output, that's not part of the actual code. The problem is on this line. So if NVRAM match, name match, return webs write WP output. All that's saying is if the key matches the value, then call this function webs write with the output string that we gave it on the WP file descriptor, or yeah, that's a file, or the file stream, excuse me. Now webs write is defined in httpd.c right here. So let me separate that out from everything else for you. So webs write is basically just a macro that is alias to fprintf followed by fflush. Now fprintf takes a format string, the file stream, and the arguments corresponding to the format string. So like if I want to print out a number, I might do %d in the format string and then give it like an integer as the arguments. Now, the thing about fprintf is even if you don't give it those arguments, if they're referenced in the format specifier, fprintf and printf and like all those, as well as sprintf, all those kinds of functions are going to expect those arguments in the places where they're supposed to be based on the calling convention for the architecture. In this case, this is an ARM device. It's a 32-bit ARM v7 little endian device. So the calling convention is the first arguments go in registers R0, R1, R2, and R3. So that's the first 4, and then the rest go on the stack. So if I give fprintf just the format string, let's say, let me write that up really quick. So if we call fprintf with %d and then the integer I, then it's going to expect I in the register R0. Now the catch is, even if I don't give it I, it's still going to think there's something in R0. And it's going to try to read from it and print it out to the file stream. So if an attacker is able to control the format string that's being passed to something like printf or fprintf, then they can put characters like %d to read an integer, %x to read hexadecimal bytes, %p to read pointers, in this case 4-byte values. And since those values aren't given anywhere in this webs write call, they're going to be read from the registers R0 to R3 and then from the stack. And that turns out to be exactly what the developers did wrong here. OutputIt, which is an attacker-controlled parameter defined from appget.cgi, is being passed directly to webs write, which once again is just a macro for fprintf. So fprintf is going to take the attacker-controlled format string and use it to read arguments from registers in the stack and print it out back to the client. And let me just show you, since that's a little bit abstract, let me show you how that can be an actual vulnerability. So here's the request I made to appget.cgi. And oh, I wish I had zoomed into Burp Suite. Hopefully you can all see that. I'm going to add the required parameters to app.get.cgi, which is hook, and then the name of the hook is NVRAM match for the EJ NVRAM match handler. And going back to source, the example they provided it was WANT and Proto and DHCP. It's going to pre-selected, so that's all we need. And then the output string. So let's just do an output string of hello and send that over to the server. So we get back a response, gives us the name of the hook and the key, and then says hello, which is the output string we gave it. Now, what if we put a format string in there? Printf style, like %p. Oh, we have to URL encode % symbols. That's important. So that turns out to be %25. NVRAM match WAN proto nil. So that's suggesting to me that the register R0 currently contains a value of 0. But we can add more. Oh, sorry, I misspoke. That shouldn't be R0. That should be R2, because the calling convention would use up R0 and R1 for the WP format stream, or file stream and the format string, respectively. So that's R0, that's R1, and then our format specifiers are going to be in R2, R3, and then the stack subsequently. So now we're reading from R3, and that's also nil. Let's try to read again. This time it's going to read from the stack. And we get an actual pointer this time instead of like a nil value. 0x7e 8b40e8. That's not super meaningful to us. Let's just keep reading until we find something interesting. Another pointer, another pointer, another pointer. Let's try to read a string. Now that's actually interesting, because when we read a string, this is coming from the stack. It looks like we got some of the actual data we supplied in the request. If you can't see this, this is just showing us the format string we gave it and the text DHCP, which shows up as an argument to NVRAM match. So that's pretty cool, because it shows that we can actually read data from the request that we supplied, except this is data that lives in memory. So we're reading directly from memory. Let's try something else. Let's try %n. %n is this kind of weird specifier in that it writes the number of total sort of variables that have been written to an address that you give it. So instead of reading from something, it's writing to something that you give it. Now, I don't know what we're giving it in this case, because it's going to expect that from the stack, and then it's going to write like what, 1, 2, 3, 4, 5, 6 values to that address. I mean, that address could be anything, like it's totally undefined. So let's just go ahead and see what happens. Turns out in this case, that address works perfectly fine, because that points to DHCP, which is on the stack. Let's just keep adding those things. So that's %n, like added a bunch of %n symbols at the end. And as you can see, the response like kind of cuts short. And if we go to the application, it logged us out. And that's because the router crashed, or the web server crashed on the router, and it had to be automatically restarted. So that's pretty cool. We were able to write data to a memory location that was given by something on the stack. Now, this is a really useful ability for an attacker, because if you can control what's on the stack, like an address, and you can write to that address, then you could potentially get remote code execution. And that is one way to get like RCE with using a format string alone, but that's actually not the approach I took. Although it's perfectly viable, I would leave that as a challenge for you guys, whoever's following at home or at work or whatever. See if you can get code execution based on this format string vulnerability alone. It's going to be a little bit more involved, I think, than what I'm going to end up with as an exploit today, but I think it'll be worth it and pretty cool. So let's go into the next vulnerability. Now that we have the ability to read from the stack and the registers, let's see if we can do anything else. So the next vulnerability actually occurs in another hook of web.c, which is called delete shared folder. And this is just a handler that takes two parameters, pool and folder, which I'm highlighting. First, it verifies that both of these parameters are non-empty strings, so they have lengths greater than 0. And then it sends that to this function getMountPath. Now, this function turns out not to live in HTTPD. It's actually in a shared library called libdisk.so. So let's go there right now. Libdisk. Read mount path, I believe. Read mount data. Get mount path. So this is just a simple function, has two locally allocated buffers, and then it just calls read mount data with pool that we give it as the first parameter. So let's go into read mount data. And this function is, pretty simple. Has a couple of, again, local buffers, line, target. But the vulnerability actually occurs on line 847 with the use of sprintf. So here, device name is just the pool parameter that we gave it from EJ delete shared folder. So that's pool. And that's being written into the target buffer with a %s specifier. So that's not a format string vulnerability, but is another kind. That's a buffer overrun or a buffer overflow, because they're not checking whether device name is big enough or is small enough to fit within the target buffer. That's an arbitrary length string. All they checked was, is that a non-empty string? And it is. So that's going to be written to target, and since that's right here on the stack, theoretically, we could overwrite the program's saved return address and hijack the control flow of HTTPD if we just give a long enough pool value. So let's go ahead and see that in action. This is another hook. This time it's called delete shared folder. And this time it's not the function syntax, it's just a couple of URL parameters for pool and folder. The pool equals some arbitrary string. Folder doesn't really matter here. The overflow is in pool. So let's just send that to see if that works. And we're not getting what we expected. Let me try parentheses around after delete share folder. That's weird. Oh, right, because the router, the web server logged us out after it crashed. So now we have to add in the new authentication token. Otherwise, it's going to think that we're not authenticated. That's the same one. Oh, it's burp suite stuff. The domain name router.asus.com wasn't in my scope, so now I have to add that. I don't know why it switches back and forth between the IP address and that host name, but it's fine. So that's our new auth token. Let's try again. And we got an error. Let's see what that's about. Okay, that looks much better. So it gives us an empty response right now. And that's fine. But let's just see if we can overflow the target buffer. I'm just going to put in a bunch of A's Let's see what happens. Nothing. There we go. So once again, we get the same cutoff like we saw the last time. I gave EJN for NVRAM match the %n specifier. The server crashed because it wrote to an invalid address. So this suggests the same thing is happening. The server crashed. And yeah, I logged us out. HTTPD got automatically restarted, so we're going to have to plug in again. So that's pretty cool. We have a buffer overflow, and we can crash the server, but that's like not really valuable for an attacker because the web server gets restarted automatically. What we really want is some kind of code execution. So we're going to go into the debugger for that. Now, it's kind of a pain to debug on the router itself. So what I ended up doing is I copied HTTPD and all the shared libraries over to my Raspberry Pi. It turns out to be the exact same architecture, so everything runs without a problem. And I can use GDB and the entire ARM toolchain for that, so it's really convenient. So here, in this case, I have I'm debugging the program HTTPD, and we restart it. You can safely ignore the no such file or directory stuff. It doesn't really matter. So I'm going to go to our Raspberry Pi running the server, and good, we have apt-get.cgi running. Let's just send that to the repeater. Make sure everything's working. Cool. And let's copy the same URL string once again. Post. That's correct. Okay, I wonder why it's giving us an error. Oh, we already got a segmentation fault. So that many A's was enough to crash the server on my Raspberry Pi. How many is that? 25. Okay. So let's actually go ahead and figure out where exactly the crash is occurring. Let's make sure it's happening when target is being written to using sprintf. To do that, we can break in read mount data, which is where the buffer overflow occurs. And let's just continue. Let's just restart the server. Gonna have to set the breakpoint again. Continue. Good. So breakpoint trigger. We're inside read mount data, and let's just step. We don't have debugging symbols, so I'm gonna step through the instructions as opposed to line numbers. And then since we know the vulnerable call is going to be sprintf, let's just set a breakpoint on sprintf, and then continue until that. And then step. Let's just exit the sprintf function. And now we're back in read mount data after sprintf on the target buffer. So theoretically, if our assumption is correct about that being the source of the buffer overflow, then the instruction pointer should have been overwritten with whatever we gave as our pool value. So let's just check that. Info frame. Okay, so save PC is not exactly a bunch of A's yet. That tells us that we didn't overwrite the save return address. What about the registers? Nope, nothing there. What if I just continue? So get a segmentation fault? Okay. I'm just going to put in a lot more A's now, just to see where we actually end up crashing. I'm gonna have to restart the program once again. And then every time I restart the program, I have to reset the breakpoint on read mount data because of ASLR. It's a different address. So delete all breakpoints, break on read mount data, continue, and then send this request. Step, break on sprintf, continue, get out of there. And that's promising. Save PC equals 0x41, 41, 41, 40. And that indicates to us that we overwrote the saved return address of the function read mount data with a bunch of A's, basically. 0x41 is the hex value of A. So if we continue, it's going to end up directing the control flow to that address, and it's going to crash, obviously, because that's not a valid memory address, almost certainly. So yeah, we should probably take note of that and reduce the number of A's to see when exactly that part gets overwritten. I mean, this is a kind of tedious part, but it's important to know where exactly the return address, exactly how many bytes the return address is from the top of the stack, because that's how we get code execution. Restart the program, delete. Okay, so save PC is once again that value. So how many A's is this? 55. Let's reduce it. Let's take off like 10. Or more. Looks like burp suite's frozen on me. That's okay. We'll go back to it. I need to restart this anyway. Please cancel. There we go. Okay, so PC is not overwritten, so what we just gave it is not enough. And I think we took off like 10 or 12, maybe. 42 is not enough. So 1, 2, 3, 4, 5, 6, 7, 8. Let's try for 50. Okay, so we got 41 again. So it seems to happen between 42 and 50 characters. That's fine. We don't need to know the details for now. We can figure that out later when we actually craft the exploit. But there is one thing to note. It's that this router employs full address space layout randomization, or ASLR. So we can't just like give it the address of shellcode on the stack and then jump there. Like that would be the classic stack smashing attack, because we don't know what the address of anything on the stack is, or anything on the heap is, or really anything in the program. So that prevents us from doing a simple return to libc as well, because we don't know what the address of maybe system is going to be in libc. But that's easily solvable because we have an information leak from the uncontrolled format string. So let's go ahead and take a look at that. Okay, so sending along this format string also works on the Pi, of course, except we get some different values for the first R2 and R3 registers. I don't know why that is exactly, but it's not going to be a problem. So we have some pointers. Now these values are going to change every time, right? But based on their distance from whatever we want to go to in the actual program. For example, suppose we want to jump to system, the system function, which lets us run a shell command, and we want to give it a shell command to start telnet-d. We can just take the address of system from GDB and take this address and subtract the two addresses, and then we're going to get an offset. If this pointer is close enough to where libc is and where system is, and then offset's not going to change between runs of the program. And we can use that offset to calculate what the address of system is going to be every time we run HTTPD. So let's do some basic debugging. Print the address of system. That starts with 76CE. Now that's pretty far off from this one, which is 7EFF. So I'm going to keep reading pointers until we get something that's close to libc and system, presumably. And what happened now? Oh. So remember, all we're looking for is something that's close enough to libc, something that begins with 0x76. Hey, there's one. 76CE. That's exactly what we had for system. Time for some basic arithmetic. Print system. It's the fifth one. And we're just going to subtract these addresses, see what we get. So let's put that in hex. So that's 0x29F8. So the late pointer that we got lives exactly 0x29F8 bytes above the system function in libc. So that's pretty close, comparatively speaking, when you're considering the entire range of a process address space. So that gives us an offset that we can use for system. And to verify that, let's run the program again. Okay, so that's right. On the Pi, there's no ASLR for libc, but on the router there is. So that's a discrepancy there. But that doesn't matter because the offsets are still going to be the same, even if they don't change. So that gives us something to jump to. If we leak the fifth value from the stack, or not the fifth value from the stack, the fourth value from the stack, 1, 2, 3, 4, then we can read that pointer, take this offset, subtract it from it, and then get the address of the system. And then we can just put that into a buffer overflow payload to jump to system. Then we also need one more thing. System expects arguments in R0, since it's an ARM system. That's what the calling convention dictates. And we don't control R0 directly. We do control the stack, as I showed you earlier with the format string leak. But we need some way to move contents from the stack into R0 so that we can call an arbitrary shell command and pass it to system. To do that, we can use what's called a ROP gadget. So a ROP gadget is just a set of instructions somewhere in memory that ends with a return instruction. So it pops whatever's on the stack back into the program counter. All we need is something of this form. Pop R0 PC. So it takes whatever's on the stack, puts it into R0, takes whatever's on the stack, puts it into the program counter. In other words, returns. And there can be other registers like R1, R2, etc. in between here because we don't care about those. But it has to have R0 and it has to have PC. So let's really quickly find a ROP gadget that we can use that accomplishes that. Well, I always forget what the actual flag is for object dump. So capital S in this case, I believe. So there's nothing like pop R0 PC. So let's try something that's let's try regular expression to match something that has other registers as well. Yeah, that flag. And there we go. So there is a suitable gadget in libpthread.so, which is this shared library that I just showed you. So it pops registers R0, R1, R2, R3, R4, all the way to R6, and then the program counter, so it returns. So that works just fine for us. And that turns out to be if we go back to our GDB session, it turns out to be in this function, pthread alt lock, which has that address, and this specific gadget, this instruction, is at this offset. Right here. So that's the gadget that we need to jump to. And once again, this is the address of that, but we don't know what that address is going to be on every subsequent run of the program, so we need an information leak. Since that also begins with 76CE, we can probably just use the same pointer as before, this one, and calculate another offset, this time for that gadget. Minus this. So that's, one second, that's our next offset, negative 0x23D0 from the leaked pointer. Let me make sure I'm getting this right. So this one is R2, this one's R3, this one's from the stack. So the third pointer from the stack. In other words, we can get rid of everything else after that. In other words, the fifth pointer in total is the one we need for system and for the gadget. That works fine. So this flow is basically going to look something like this. So we're going to jump to the gadget, which is going to put something we control on the stack into R0. And then after that gadget returns, it's going to call system. Now, the command we just applied is already in R0. So by the time system is called, it's perfect. We can just execute the command straightforward like that. But we need to know the address of the command string on the stack. And to do that, we have to use the same technique as before, which is basically finding an offset based on a suitable pointer that we leak from memory. So we have a bunch of pointers, and we just need to find one that's close from the stack. Now that's going to be pretty far away from libc, so it's going to look different. It's not going to be 7.6 CE, I think it was. It's not going to be this one. It's going to be one of these or something else. But basically, we have to go back to our buffer overflow vulnerability and give it some junk data. Give it like a command string, say. So I'm going to add a bunch more A's. Actually, you know what? That's stupid. Where the command string ends up is going to depend on the size of the actual payload. So we have to figure out all the padding and stuff needed before we do any of that. So let's just get our 42 bytes of padding before the return address. Let's assume the overwriting occurs right here, and that BBBB is going to be the return address. In other words, 42, 42, 42, 42. And then, so that's going to be the address of the gadget. The gadget is going to take, what was it? 1, 2, 3, 7 registers, and then the next address to jump to. So that's going to be 24 bytes. In this case, CCCC is going to be the address of our command string, because that's going to be what's popped into R0, and then the rest can just be junk. So 1, 2, 3, 4. Hopefully that's 24. Yep. So then after that, we're free to like give the address of system. So let's call that D for system. And then assuming that's all we need, after that can be the command string. We're going to call that testing command string. Once again, I'm going to set my breakpoints. Step. Continue until sprintf, by which point we know that the overwriting has occurred after sprintf returns. Finish. Make sure everything is what we expect. Okay, so that's interesting. Save PC isn't exactly what I thought it should be. It's 43, 43, 42, 42, which is not BBBB. That's CCBB. So it looks like the amount of padding is slightly off. So I think we need 2 more then. 2 more A's in the beginning. Let's restart again. Issue the request. Break on sprintf. I mean, this is pretty repetitive after a while, but this is how you do it. Great, so now we have all the 42s. So everything lines up just fine. Now, since from earlier I saw some of this data on the stack, I'm going to assume that the command string is going to end up towards the bottom of the stack frame. So I'm just going to examine around the stack frame and see if any of those strings shows up. Oh, so the frame is it's right here. Right here. So a bunch of 41, 41, that's a good sign. Let's print these as strings to see if we can isolate the command string itself. Cool, we can. So we have first, before the testing command string part, we have 4 C's, A 24 times, and then 4 D's. So we do this plus 32, that's testing command string. So this address exactly is where our command string, in theory, to pass to system and then run the shell would end up. I'm going to copy that, put it back into Python. And then, so this starts with 7EFF. Let's go back to our information leak, see if anything matches that description. This one does. Copy that. This offset is 0x2038, so it's a positive 1 instead of a negative 1 this time. But it's also the last offset we need in order to craft an exploit, so shows we're making progress. And we basically have the full payload structure, like in principle. It's all of this stuff. And we just need to fill it in with meaningful values. Let's go ahead and see if, just do a dry run, see if we can give it the hard-coded values and get it to execute something like a command of our choosing. So we said that the gadget was here. So let's encode that address and put it in. That's going to be a little tricky. Use Python for that. So all I'm doing here is writing the code to make a GET request in Python for the same endpoint that we've been using for the buffer overflow this whole time. I'm just using Python because that's going to make it easier to encode hex values for addresses. Luckily, this is Python 2, so we don't have to deal with like all that string encoding and stuff. We can just concatenate bytes directly with addresses. So the string is going to end there, I believe. Then's going to come the address of the gadget. That would be this one right here. So it's going to be backwards because of the endianness system. Seven six CE AACC. That looks right. And then, so that's a gadget. And then the next one would be this thing on the stack, which, I mean, it's hard coded for now. So it's this one. Then comes the padding for the gadget, 24 bytes of garbage. And lastly, the address of system. It should be this one. Yeah. Sorry, I just don't want to make sure. I want to make sure I don't get any of these bytes wrong, because that could have pretty bad implications, like the whole program crashing on me. 76 CE B0 F4. Yeah, it looks right. And for the command string, let's just do something simple like not reboot. How about let's do a non-existent command, and that way we'll see the output on standard error in GDB and make sure we're not missing anything. So let's just do some garbage. And I think that's right. Send over. Request is not defined, of course. Import request. Can't decode byte position 113. What did I do wrong? Well, that's wrong, first of all. That's wrong too. And that one. Wow, I made a lot of mistakes. Maybe I should just cast that to a string. Maybe I was wrong. Maybe we do have to deal with the encoding stuff in Python too. Let's put everything as one giant string. Simplify things. Oh, still not working. So it expects a UTF string, I think, UTF-8. Still no dice. Let me try struct.pack. This would be int, maybe? Okay, let's try that. Let's try putting in struct.pack values instead of just concatenating these bytes. Invalid syntax. Wow, that is usual. Well, what do you do when anything goes wrong? You just Google it, right? Probably something very simple when it's doing wrong. You decode UTF-8. Try to encode before. Okay, in the interest of time, I'm just going to go ahead and show you what I did to make this work. What about it? Percent encoding. I mean, I really don't know why this isn't working now. It's probably something very stupid. So I may have just been handed some assistance here. Let's see if this helps any bit. Let me try something. Let me separate this into parameters. because I don't think requests can take non-UTF-8 things in the URL. So what I'm doing right now is I'm just separating parameters in the URL from the actual path to make it easier for myself and to see if I can try different encoding with those. Close that curly brace. Apparently what we need to do is encode these, prefix these with B to indicate bytes. And then for these binary values, we should encode them as UTF-8. Let's put this into the code editor to see what syntax error I inevitably made. Wow, the whole thing is red. That's not good. Missing a quote, of course. It's always the simple, stupid things. Called syntax now. No, Python, I'm pretty sure this is right. Let's try Python 3. I've been reliably told that it's the superior language, so hopefully this works in that. So it looks like something's working. Just have to continue the program. Oh, segmentation fault. Restart it. Send this over again. Breakpoint triggered. Continue after that. Breakpoints. Continue. So that's not the address I was expecting. Something else. Oh, well, what do you know? We made it into the system function. It seems like the command string is wrong, though. That address needs to be fixed. We debug that. 76CE. This one's the gadget, this one's the command string. So I'm just going to print out that address, make sure that our garbage command is actually at that location. Not, then did something wrong. Okay, so it's a little bit off. It's off by 6 bytes, it looks like. So let's try again. Same error. So it ends up getting an invalid address somehow, instead of the one we want for the command string. So I'm setting a breakpoint on system to, wow, it didn't even go to system that time. Just making sure everything's the same address as before. Thread alt lock plus 108. Should be CEAACC. That's right. So it looks like it never even went to the gadget. Maybe I messed something up in terms of the payload with all that encoding troubleshooting. It's really weird. Shared folder. You know what, let me proxy this through Burp Suite so we can get a better idea what's going on. Not that. So it should have just made a request in here. Burp's being slow. There we go. So without any of this, it should take us back to 42, 42, so on. No? It was 45 characters. Okay, so it looks like there was some alignment issues with the save return address. Continue, delete. Finally. Okay, so it all boiled down to not getting the number of bytes before the return address right. So if I'm reading this correctly, got one of the B's and the rest were A's. So need to delete 3 of these to make room for the other B's. Run it again. Great. So that's the proper number of A's and B's or whatever. except instead of B, we need a gadget address. It's this. Still not working, huh? C2HC320. That's not anything that I gave it. Maybe this, oh, this space probably messed everything up. Yeah. Even though that might not be the actual problem here. Oops. Delete that. 76 CE. What is that? That's the gadget. Except it's not the right one. Looks like we're off by 4 there. Or we're not even close to it. This is a real pain. Sam, are there any questions or confusions going on?
Let me take a look.
Okay.
One person was curious about when reported got back.
So this was found, I believe, in July, and we reported it in August, and they got back to us pretty quickly. Our last communication with them was, so they got back to us way back in August and September, and they fixed it back then. Our last communication with them was about 3 weeks ago, asking them when they were going to push a firmware update for this specific device, but they never got back to us about that. So right now I'm just going through the really annoying process of troubleshooting, seeing where this payload is going wrong. I want to make sure the gadget is actually being hit. So I set a breakpoint on it. Doesn't look like it's being hit. Really weird. That's not even the right address for it. Let's check out what the stack looks like. I mean, everything we sent should be on there. So that looks like where it's messing up, because I don't want that as my return address. Wonder where that's coming from. Okay, wow. So changing that to struct.pack worked, because that looks exactly like the address of the gadget. So I'm just going to do that for every single one of these addresses. Hopefully we can finally get this out of the way. Move on to making an actual exploit. struct.pack. So basically all struct.pack does is it takes an integer or something that you give it and converts it to a sequence of bytes. So in this case, I'm taking this integer, which is basically an address, 76CE0F4, and I want to convert that to a series of bytes that we can send along. And concat bytes to stir. Oh yeah, you need to add the B prefix to these things. Wow, so looks like we got something. It says SH or sh, KSFDG not found. So that looks like a part of our command string that it tried to execute. Where is it? Right here? So I think for some reason I changed the address of it. I added 6 to it because I thought that would work, but no, this is right. So now we have the ability to run commands. Let me just put in like a test thing, like ls, see if we can actually repeat our success. Awesome. So as you can see, we get a whole bunch of ls output after supplying the command string ls-la. So it looks like we can actually get command execution via this way. Now these are hard-coded addresses. What remains to be done is to take the addresses from the information leak and convert those to, or not convert those, use the offsets to compute the addresses that are going to be used in a subsequent run of the program. To do that, I developed a simple Python script, which I'll bring up in just a moment. So here's the script, and I'm going to walk you through what it's doing on pretty much each line. It's not that many lines. I think it's about 40. So here we go. So first I define these offsets: gadget offset, system offset, command offset. You may recognize these exact numbers from earlier. Well, that's because they're the same ones. This one is to the rock gadget, which is above, pthread alt lock plus 108. All that does is pops R0 and then R1 through R6, but we don't use those. Then returns. Then here's the system offset. That's just the system function in libc. And here's the offset to the command string on the stack. Once again, it's a -1, 2038. So my program just takes a couple arguments, host for the host and then the port, and then the username and password. Since this is an authenticated attack, you need a password for the admin account to be able to do this. Then it creates a session for requests. That's just so I can keep the session cookie across different requests, so I don't have to keep sending my cookie each time manually. Makes a post request to log in, gets the auth token. Here comes the fun part. This is the actual leak. So it makes the request to appget.cgi with these parameters. The nvram match hook, as we saw before, our old friend, with 1, 2, 3, 4, 5 pointer specifiers. Now we're only going to use, in this case, I believe the third and the fifth one. So after printing that information leak, just for debugging purposes, we take the fourth, well, index from 0. So the fifth value, the last value, we take that pointer and we convert it to an integer. Then we do the same for the third. And those are our like base addresses for the shared libraries in the stack, respectively. Then we just basically do like the same process as earlier, except in a more automated way. The gadget lives at the base address for standard library, or not standard library, shared libraries, plus the offset that was computed earlier. And same for system, same for command. So it's just taking those base addresses and adding them to the offset to get what they're actually going to be next time the program runs. And then this is just a simple like check, because if there's a null byte in the payload, like suppose there's a 00 byte in one of the addresses, which happens sometimes, we don't control that. It's just something that we're going to have to deal with. Then the exploit's going to fail because HTTPD reads using, it writes into the target buffer using sprintf, which works on C-style strings, which means that like null bytes are terminator characters for strings. So when it sees a \x00, it's going to say like, oh, that must be the end of your string, even though there's more that we still have. And it's going to like write some invalid payload and then probably crash. So we have to deal with that. And then the last step is just making the final request to the buffer overflow vulnerability endpoint and then filling in the payload with the various components that I manually constructed earlier, which is 44 bytes of padding using A, the address of the ROP gadget to put our stack controlled contents in R0, the address of the command string, which is what's going to be placed in R0, 24 bytes of padding for R1 through R6, the address of the system function, and then our shell command, which in this case is telnetd for starting a root shell on port 6666. And then it just prints the content for debugging once again. So let's just try this. We can try this on both the, we could theoretically do this on the Pi and the router, but Pi doesn't have telnetd installed, so it'd be kind of pointless. So let's just do it on the router. So we give it the address of the router, which is 192.168.111, a port number, in this case it's just 80, username, and password. So it prints out an information leak. And now it hangs, which is a good sign, because that means the control flow of the program was interrupted to run the system command and launch telnetd, which by default doesn't fork into the background, so it's just gonna live in the foreground and cause HTTPD to hang. So let's see if we can actually telnet into there. Port telnetd. Cool. So, I mean, yeah, we don't have ID, but we don't have who am I, but you know, whatever. It's a root shell, and it's on the router. Basically, I have full access to the system now. Yeah, we could, I think, could Control C that other thing, if I haven't already. And then it still works, like it doesn't affect our usage of telnet at all. But yeah, that's pretty much the long and tedious and really complicated process of developing this exploit. So if you have any questions, just feel free to post them in the stream and I'll get to them. If not, thank you for watching.